Okay, so in the last segment of the course, we saw probabilistic context-free grammars, PCFGs. We gave basic definitions of PCFGs. We saw how to estimate a PCFG from a tree bank. And we saw how to apply a PCFG to a new test sentence using the dynamic programming algorithm, the CKY algorithm, to recover the most likely parse tree for a given sentence. So let me just give some historical background. The first tree banks were created in the early 1990s. So the early 1990s was the first time we had data of this form from which we could learn, for example, a PCFG. And when these resources became available, it was very natural for people to consider PCFGs. PCFGs have actually been around for a long time. They've been known since at least the 1960s. And so people immediately applied PCFGs, basically in the way I showed you in the last lecture. But the performance was really quite poor. Roughly 72% accuracy, at least on the Wall Street Journal tree bank I was talking about, where this accuracy is the accuracy in recovering basic subparts of parse trees, basic constituents within parse trees. So if you look at parse trees with this kind of accuracy, they are really, really quite poor. PCFGs were quite a disappointment. Modern parsers perform considerably better. Around, again, for the Wall Street Journal data set I was talking about, low 90s in terms of accuracy, on English at least. So what I'm going to do in this next segment of the course is describe some properties of PCFGs which really explain this low number. Two critical weaknesses. One is lack of sensitivity to lexical information, and two is lack of sensitivity to structural frequencies. But we'll then go on to formalisms such as lexicalized PCFGs, which build very directly on ideas from PCFGs and yet have much more, essentially have state-of-the-art performance. So we'll see that while raw vanilla PCFGs perform very poorly, it's possible with some refinements to PCFGs to build a modern parser with state-of-the-art performance. Okay, so let's start talking about these weaknesses, taking each of these two things in turn. So let's first talk about this problem of lack of sensitivity to lexical information. And we'll first look at the independence assumptions made in a PCFG and see how they lead to real issues in this respect. So here's a very, very simple tree. And as we saw, the probability of this tree is going to be a product of terms, one Q parameter for each rule that we see within the tree. And what is striking about PCFGs is that they make very, very strong independence assumptions. In particular, if we look at the choice of any particular word in the tree, then once we condition on the non-terminal above that word, i.e. the part of speech, the assumption in the PCFG is that the choice of this word is conditionally independent of everything else in the tree once I condition on the part of speech. So we're basically making the assumption that the part of speech carries all the information you could possibly need about the identity of this word under that part of speech. So that is an extremely strong independence assumption. We've made the assumption that this word is independent of everything else in the tree once I condition on this non-terminal, and in particular that this word is independent of the other words in the sentence. And this is an extremely strong assumption, and it's a very bad assumption for natural languages. So let's look at a couple of examples where this independence assumption leads to real problems. And we're going to first start with a case of prepositional phrase attachment ambiguity. And so the sentence here is workers dumped sacks into a bin. And there's a prepositional phrase here, into a bin. And there are two possible attachments, hence two possible parse trees. In this first parse tree, which is actually correct, the prepositional phrase attaches to the verb phrase dumped sacks. In the second parse tree here, the prepositional phrase attaches to this noun phrase sax. Okay. So now if we look at this example more closely, we can list the context-free rules which are seen in the two trees that I just showed you on the previous slide. So this is the list of rules seen in the first parse tree, and this is the list of rules seen in the second parse tree. And the first thing to note is that many of these rules are actually identical. In fact, the only way in which these two parse trees differ is in the choice of a rule here, VP goes to VP prepositional phrase. This was actually the VP attachment of the prepositional phrase. And here we have NP goes to NP prepositional phrase. So if you think about the way we calculate the probability of each of these trees, we simply multiply together the probabilities of the individual rules. And so the decision as to which of these two trees is more probable is going to come down to just these single parameters corresponding to these two rules which are different. So essentially, if the Q parameter for NP goes to NP prepositional phrase is greater than Q of VP goes to VP prepositional phrase, then this tree will win, otherwise this tree will win. So the entire decision between these two trees comes down to these two parameters, and the attachment decision is basically made completely independent of the words in this particular string. So if we look at prepositional phrase attachment, this is a spectacularly bad thing to do. And let me give you a bit of context here. So let's look at the four main words in this attachment decision. So dumped, sax, into bin. So this is a verb. This is the first noun, so I'll call this N1. This is the preposition. And this is N2. So statistically speaking, if you make a decision without any knowledge of the words, i.e. you always go for a noun phrase attachment or you always go for a verb phrase attachment, you might get around 55% accuracy in this attachment problem. So you might get around 55% of the attachments correct. That reflects the fact that, in fact, there are pretty much the same frequency of noun phrase attachments versus verb phrase attachments, maybe a very, very slight bias towards one or the other. If, however, you look at the four words involved in the attachment decision, you can get up to around 84% accuracy, which is still not perfect, but is considerably better. It's not perfect because prepositional phrase attachment ambiguities are still a very, very difficult problem. But we can nevertheless do much, much better than the accuracy here. This goes back to work in the early days of statistical parsing, where people considered just this isolated problem. Given four words, can I predict whether we attach to the noun or the verb? And they used various machine learning methods for this. And they used supervised data, so examples like this, with a label. So the label in this case would be the verb label, because this is a verb attachment. You would collect a few thousand examples like this and then see if you can use machine learning to make the prediction. If you ignore the words completely, you do really rather badly. If you build a classifier that actually looks at the words, you can do much, much better. Anyway, bottom line, PCFGs make this decision without any reference to lexical information. It's completely independent of the words, and we know that this is a very suboptimal decision in this case. Here's a second example. This is a case of coordination ambiguity. So here I have a phrase, dogs in houses and cats. And there's an ambiguity as to what this noun phrase cats is coordinated with. So in this first example, it's coordinated with dogs and houses. And in the second example, it is coordinated with just houses. So another classical example of ambiguity. These kind of coordination ambiguities come up everywhere. Again, we can play this game where we simply list the rules in the two analyses that I've just shown you. And in this case, we see the following. So here are the set of rules in the first analysis. Here is the set of rules in the second analysis. And the rules are actually identical. We have exactly the same set of rules in the two parse trees that I just showed you. And so because of this, they have to have identical probability under any PCFG. So there is simply a tie in this case between the two different parse trees. So even though the parse trees apply the rules in different orders, that's how we get different analyses, the set of rules in the two parse trees is the same, and so the probabilities in the two parse trees has to be the same. And the PCFG completely fails to display a preference for one parse tree or the other, and in particular it completely ignores the lexical information. So that's a couple of examples where ignoring lexical information leads to real problems. There are many, many others. But let me go on to the second cause of problems with PCFGs, and this is a failure to model structural preferences. This is a phenomenon called close attachment that I'm going to show you on this slide. So let's assume we have some sequence of words, noun, preposition, noun, preposition, noun. For example, we might have president of a company in Africa. And again, we have a prepositional phrase attachment ambiguity here, because this prepositional phrase in Africa could attach to the most recent noun, company, or it could attach to this more distant noun, president. So we either have a company in Africa or we have a president in Africa. That's the ambiguity. And here we have these two structures. This is the close attachment. So I should have said this attachment where the prepositional phrase attaches to the closest possible attachment point is called close attachment. And in this second example, we have attachment to the further noun. You can verify that both of these parse trees have exactly the same set of context-free rules, and therefore, again, receive identical probability under a PCFG. And so the PCFG fails to distinguish between these two things. But if you look at the statistics, this first structure, close attachment, is significantly more frequent than the second structure. It actually occurs about twice as often as this second kind of structure. So even before you look at the words, there's a fairly significant structural bias for these kind of close attachments as opposed to these further attachments. This close attachment preference becomes even more pronounced if we look at examples involving attachments to verbs. And this is actually an example sentence which I'd shown you earlier in the class. So the ambiguity here is that the prepositional phrase by Bill can either attach to shot, this is the close attachment, or it can attach to believed. So in the shot interpretation, Bill is doing the shooting. In the believed interpretation, Bill believes that John has been shot. Okay, so there's two possible analyses. Humans, I think, would have a very strong preference for the shooting analysis. They might not even see the believing analysis in this case. If you look at a PCFG, you will see that these two analyses, again, have identical sets of rules. And so the PCFG, again, is going to assign the same probability to both of these analyses. However, if you look at this kind of case where a prepositional phrase has two different verbs which it can attach to, the close attachment is, at least in the Wall Street Journal data we have, about 20 times more likely. So there's a very, very significant statistical preference for the close attachment here, which the PCFG completely fails to capture. Okay, so I've outlined some weaknesses of PCFGs, lack of sensitivity to lexical information, failure to model these kind of structural preferences. In the next segment of this course, we're going to look at refinements to PCFGs which fix many of these problems and lead to much more accurate parsing models.